welcome. There we are. So this hints for the workshop, or the workshop questions, I should say. B1 to B3. So in principle, B4, 5, 6 are done in the workshop, and you're supposed to do these at home from week 2 onwards. So this is week 1, 2. What's the question? Given x is 1 is a critical point of the function, find all critical points and characterize them. So given f of x is a 4th order function, so we have to filter out to find the critical points. So first we are given f of x, so you can write that out. And to get the critical points, we need to derive f prime of x, which is x to the power 3 minus 3x plus 2, and that is, this is 0. So then we are given that x is 1 is a root, so we take out the factor x minus 1. Well, and then we see that this one needs to be x squared, because x times x squared is x to the power 3. That is, last one is plus 2, so this needs to be minus 2. And then we need to figure out what the middle one is. Well, minus 2 times x is minus 2x. And though this needs to be plus x, because times minus 1, that gives us the 3x. And then this one goes further. We can factor this out as x minus 1, x plus 2. Is that correct? So that's x squared minus x plus 2x minus 2. So that means that the roots are x is 1, 2 times, and then x is minus 2 are the critical points. So when you're given one of the roots, then with a cubic you can always find the other roots, because you can take out the quadratic and then use the ABC formula, or when you see it, you factor that one out as well. So that's this one is a double root, because this x minus 1 squared. And so now we need to find x double prime of x. So you find that, and then what you are going to do is the following. The first term here is 1 over 4 x to the power 4 plus other stuff. So you know that for large x, f of x is very large, in fact goes to infinity. So for also for large negative x, since x to the power 4 is even function, is also very large. So that at least you know. So now you need to find f prime of x, and now you want to calculate the values f1 for the double root, f2, but also yes, that's right. So calculate those, and then also f prime double prime of 1 and f double prime of 2, to see whether it's positive or negative. Since it's a double root, we expect f prime to be 0, so we can already say that, and then we need to find out what the sign is of this one. So when it's positive, so when it's bigger than 0, it's a minimum, and when it's less than 0, it's a maximum. I can never remember the signs, so what I always do is I take x squared, and then I know that the double derivative is 2, so that's bigger than 0, so an x squared looks like this, so it's a minimum, and then minus x squared has as a double root minus 2, and I know it looks like this, so I know it's a maximum. So that's so I always use x squared and minus x squared to remember the signs. But now you have a lot. Now, so you need to calculate that. Now you have a lot in hand because you can plot f1 and f2, so you know where that is. You know that this is the saddle, so here and here we are with 1 and 2, and this is x and this is f. And you know whether in 2 it's a minimum or maximum, and you know that it comes from very high. Oops, I shouldn't do that. Why is it do that? It comes from. Oh, am I off the? That it comes from very high, then goes somewhere, does a little thing, and then it goes up. So that's what you need to figure out. And then in this case, I would also calculate a simple point like f0, and f0 from the question is just 1, so it's just a simple point. And if need be, you try to find more point. But there are so 3 values, f1, f2, and say f0. Then you know that very large, very negative but large, and very positive and large, the function goes to in plus infinity. So somehow so if 0 is 1 here, then you know that here it's going up a lot, and here it's coming somehow coming down, and then in the middle, what it does in the middle depends on what whether the f of 2 is a minimum or not. And then this point is of course a saddle, so it's neither a minimum or maximum. The slope is 0 because it's a critical point, but it is a saddle. Right, so that's that one. Where are we? Preview. No, the second question is draw a contour plot of the function set x squared minus y squared in the xy plane, and sketch a graph of this function if possible in the 3-dimensional plane. So first set, so this is number 2, x comma y is x squared minus y squared. We want contours, so that's C. So then you take a couple of convenient C's. So C is 0, gives us y is plus or minus x. So then you know plus or minus x is this and this. So and then for, let's take C is 1. For C is 1, what do we get? We get, we bring y squared to the right-hand side. So y squared is x squared minus 1. Y squared is x squared minus 1. So that means that y is plus or minus square root of, what is it, x squared minus 1. So if this is y and this is x, so if y is 0, so y is 0, so that's on this axis, then x is plus or minus 1. So this plot is a bit rough, but these 2 points, these 2 points are there. So now we know that the sketch is a bit rough, but it goes to the asymptotes, then here it's vertical, and then, oops, and not with a wobble, then it goes there, and here it goes to the asymptote. Because for very large x, positive or negative, the -1 is negligible, so it asymptotes to this one, y is plus or minus x. So I had here, if y is 0, then x is plus or minus 1. So we can also put that back in the top one for C. So let's just check, or in this one. So if y is 0, yeah, y is 0 is x is plus or minus 1. So for C is 4, I get y squared is x squared minus 4. So y is plus or minus square root of x squared minus 4. And I choose C as 4 because now if y is 0, x is plus or minus 2. So I'm going to choose a different color. So then I'm here, I suppose 1 minus 1. And this is 2. So we're now the same. For larger and larger x, it asymptotes there. So this black line should actually, my sketch is a bit rough. This black line should of course asymptote to the asymptote, and then the red line also asymptotes, but a little bit slower to that one. And here it goes up, oops, ups, and then it asymptotes up, and it doesn't pass, of course, and so forth. Right, so now we have the gist. You have here it's vertical, and then it asymptotes. Here it's vertical, and then it asymptotes. So we don't need to. So that's how it is. Am I doing that right? Yeah. But now I have to be. So that's for C positive. That's for C positive, and C is set. But now I have to take C as -1. Then I get y squared is x squared plus 1. So it's better to do x squared is y squared minus 1. And that gives us x is plus or minus y squared minus 1, which means that if y squared x is 0, y is plus or minus 1. And those are these points. But then again, for large x and y, this asymptotes. But now I really should have used different colors or dashed lines. Now, here set is bigger than 0, set is bigger than 0, because C is bigger than 0, and here set is less than 0. Here set is less than 0, etc. So I would do more. So here, in this region, when you make an XY set graph, it goes into the plane, and here as well, and here, because set is bigger than 0, it goes out of the plane. So what we have is a saddle. It comes from, if you go to the negative y-axis, it's very low, then it goes to 0 at y is 0, and then for positive y, it goes down. But along the x-axis is different. You have for large x, it's very positive, and you dip down to 0 at the origin, and then you go up when x becomes large and negative. And on y is plus or minus x, z is 0. That's where from the negative set it changes to the positive set. So make the 3D graph yourself, realizing that here it goes into the plane. That's where set is negative. Here it goes above the plane. Set is positive because set is C, right? Set is C. And then on the asymptotes, Here, y is plus or minus x. C is 0, so z is 0. There, the behavior changes. Oops, I have to find the next page. What do? We go to this one, and we go to B2. What do we need to find? We need to find the, am I there? We're there. We need to find the derivatives. So B2, 1 and 2. So you need to calculate f of x, which is df dx, while keep y fixed. So y, for all intents and purposes, is constant. So y to the third in there, you just keep it constant. So you just take it with respect to x. So that's 2x, and y is third, just a constant, because y is here, right? While taking the derivative with respect to x, and this is 3x squared y to the power 5. And likewise, fy is df dy, and then put it between quotes, right? Because it's not keep x fixed. And you do the same here. What do we do? 3x squared y squared plus, what is it, 5x cubed y to the power 4. And now fxx is second order derivative with respect to x squared, so that's the d dx on the outside on df dx. That's what it means. Well, so call this q, say q1, and this q2. Then this is the d dx of q1. Q1 is just a function of x and y, so you do the same thing. If you don't need to do this, but it's just to realize that you have already calculated this, and you take the d dx of what you have already calculated. So you have to calculate it first. For fyy, you do the same, but for fx sub y, I have to be careful. What with Young's law, it's so the y is on the outside. So now it's d dy df dx. So that's d dy of q1. You don't need to introduce the extra variable, but it's just to emphasize that you've already calculated df dx, which you could define as q1, functions q1 of x, y, and q2 of xy. And this, of course, as a check, should be fyx. So, but then you take the dd. When I'm doing this, yes, the ddx, the one on the outside, and then the one on the inside. So that's all what you need to do, right? And then 2, I leave 2 to you to do. If you, so if you, when you take the derivative of the log, which has argument dx dy, so you have to be a bit careful. So df dx is fx is 2x sinus squared y minus ln xy, so that one is easy, and then minus x, and then it's d log xy dxy, and then dxy dx, right? So that's 2x sinus squared y minus log xy minus x over xy, and then that's times y So that's just one. Right? So you use here the chain rule. Oh, of course, you use the chain rule everywhere, but with the polynomials, it's easier. You don't really need to do it explicitly because you can take the y when you take the x derivative. What is it? Come on. Yes. You take the y. It's easy to say. See, the y just stays a constant. So I leave 2 further to you. Do make the check that fxy is fyx, because there are no Young's theorem. There are no surprises there. There's nothing untoward in the function saying it's continuous. So let's go to B3. Let me first get the question up. Question, find the grade. Oh, can I do fit it up? Find the grade at a given point and calculate the directional derivative in the direction of the function u and interpret your results geometrically. So B3(1), we are given that x, so calculator, so the directional derivative is du of f, which is the definition is grad of f with inner product with u, and then the given u. So u is given as 3/5 minus 4/5, and grad of f is a vector with a little bit. Really, I should write column vectors as I said in class, or say now, but a bit lazy. They're row vectors, as long as you understand the inner product. So first I need then, and I need to do that in the point. In the point, what does it say? X comma y is 1, 2. So I first calculate df dx. What's there? X squared. Is this anything exciting? It's 2x plus 2y over x cubed. And I can write away 1, 2, right? That gives us 2 plus 2 over 8. Oh, doesn't look too nice. That's right. No, oh no, I'm doing it wrong. Oh, completely wrong. It's 2x, so that's 2 plus 4 over 1. Plus 4 is 6. Fy is, what is it? X squared is minus 1 over x squared. If you evaluate it at 1, 2, it's minus 1. So that means that grad f is in 1, 2 is 6, minus 1. And now I can calculate the directional derivative. Du f in 1, 2 is 6 minus 1. I already was column factors, sorry. And then 3/5 over minus 4/5 is 3 times 6 is 18. So it's 18 plus 4 over 5, right? So this is inner product. So the outcome is a scalar. This is 22 over 5. That's the directional derivative. And what are we supposed to do? In 2 we have to, so 2 is similar. So you have x, y. You were going to evaluate in the point 1, 1. That looks like a nice point. You have to calculate g of x and g of y, then make grad of f and grad of g, sorry, and evaluate it in 1, 1. So you get two values there, and then you have to take the inner product. So then you take the u g, so that's grad g times u, evaluate in 1, 1. So 1, 1, but the factor u is st, because you have to calculate the st for which is a maximum, a minimum, or 0. Remember that this is also defined as the molars of grad g, the molars of u, which is 1, times the cos of theta, where theta is the angle between grad g and u. So when theta is 0, grad g is aligned with u, or u is aligned with grad g. That's a better way of saying it. When cos theta is -1, it's opposite. And when cos theta is 0, they're perpendicular. So DIY, finish that. And of course you will get the answers, full answers worked out of the workshop questions on the Tuesday in the week before the homeworks are due. Yes. So thank you very much. Have a nice weekend. Oops, and I did, as usual, fall off the screen. So just to emphasize, we calculate grad g in 1, 1. Then we find du, the directional derivative, du of g. So that's grad g in 1, 1 in a product with u. And that is, remember the definition, the molars of grad g times the molars of u, which of course is 1. The molars of grad g is not necessarily 1, times cos theta, and theta is the angle between grad g and u. Of course, u is given in terms of s and t. You have to determine the s of t, which makes it a maximum, minimum, or 0. It's the angle between the two factors. Enjoy your weekend.